Okay, hello to anyone who joins remotely. Okay, there are slides from this material on the website, but I'll just, I think I'll do mostly on the piece of paper, and you can look at the slides just to compare, right? Okay, so. Try. I think it's out of focus, right? Okay. Oh. Okay, maybe it's this thing. Oh no, it's not focusing well, right? It's not just my my impression. Is that correct? Yeah, it's blurry, right? I don't know what. Okay, let's try it. There's like a moment of clarity. Damn. Something stopped working. I don't understand. You know, everything is the same as always. Okay. Maybe if I just get closer, then it will start. There's this moment when it's clear. Oh, okay. You know what? I don't know what's going on. Why this clearly stopped working, but there is a solution, which is to actually go back to my slides. Okay, and just use the slides. So that's what we will do. Because this is something is malfunctioning with this document camera. Just orient myself. So. Okay, I'm almost there. Okay. Okay. So let me do share. Oh, okay. Yeah, that was a good idea, Ryan. Put the center in it. Okay, so let me try to do what Ryan is suggesting. I just see his text right now. Oh, okay. Thank you. Okay, that worked. All right. So let's continue with this. Okay. So we did we motivated chosen ciphertext attack security by active attacks on encryption, and we said that the problem is achieving it, that all modes that we know, so we solved it for a counter mode that was in class, and CBC, OFB in homework, that you can that the problem is malleability. Attacker can take a challenge ciphertext, modify it, and if that was decrypted, he would learn the plaintext in the challenge ciphertext. So we will stop this by authenticating messages. But authenticating messages is not just a way to help achieve stronger probability of encryption. It's a goal on its own, right? Because you have a communication scenario. Alice and Bob still share a key, just like in the case of encryption. And Alice has, her application says, please send M on this secure channel to Bob, right? So is there some transformations she can do to the message such that Bob will only output M if it was sent by Alice? And if not, then he will output bot, which this is a special symbol we call bot, which stands for rejection. Okay, so he refuses to decrypt. So what is this that she could send? So Mac, which stands for message authentication, and for some historical reason, this is called not scheme, not algorithm, not protocol, but code. Okay, so it's really scheme, algorithm, etc. It's a triple of for message space M and key space K. Is a pair of algorithms, basically sign and verify, with the following semantics. Sign, given a key and a message, outputs something we call a tag. And verify, and it does so for every key in a proper space and a message in the space where he's supposed to sign in. Of course, eventually we want the space to include all bit strings, but we might not achieve this at first, similarly as in encryption case. Verify takes a key, a message, and a tag, and outputs a bit. 1 for accept, 0 for reject. Okay, which, by the way, I just you can also say this. Okay. So she will run. She will send message and a tag, where T is output of a sign algorithm on KM. And this signature algorithm producing the tag could be randomized. And Bob will do this. So he will substitute this by if the verify algorithm given key K, M, and T outputs 1. Okay. So that's how this Mac scheme is supporting authentication. Correctness, of course, for every key in the space and for every message in the space, if Alice generated a tag by signing this message with the key, then Bob is going to accept. So Bob will output 1. Okay, so nothing that was correctly signed will be rejected if it's verified under the same key. And by the way, this algorithm is also sign is sometimes called Mac. To distinguish message authentication codes from public key signatures. So macking, is creating Macs, and the tag also sometimes even that thing is also called a Mac. Okay, so you have a complete, three things are called Macs: the scheme, the algorithm to create signatures is called macking, and then there is like verification algorithm for that. And also the outputs themselves are called Macs. Okay, so to avoid confusion, I just I called it signature. Okay, but I think the book calls it a Mac. Okay, so what about security? Okay, so here's this is called chosen message attack. Unforgeability. Property. It says that for every efficient algorithms A, the following game he should lose, okay, the attacker. So A is an attacker. Here you have a good party who picked a key from the space that they were supposed to pick it from. So they just chose a random key. And this guy says, you know what, this is called chosen message attack, meaning attacker will say, please give me a tag on message M1 of my choice. The only thing is that this has to be in the message space, or otherwise this signer will refuse to create, his code will just not work. But if these things are in proper spaces, then this guy is gonna send to him the tag, which is a signature algorithm applied to K and this M1. And now he asks again, okay, so how about I wanna see also the tag for M2, and he will see this tag for M2. And so this conversation continues, right? You have some sort of Q chosen message attack queries for Q, which is a polynomial in the security parameter, as usual, right? It's we only consider efficient attackers, so they cannot query this, say, exponentially many times. And when he's finally done querying, he outputs two things: a message and a purported tag. And we say that A wins if two conditions hold. First of all, the verification under the same key on this message and a tag actually says 1. So this is a successful forgery of a successful tag, right, on message M star. But secondly, it's not trivial, meaning M star is not one of these that were signed for him.
Professor, can you move the page up?
Oh, yes. Okay, I hope this is not gonna be slow. Thank you, sorry. Okay. Yeah, thank you. So, right. In other words, and then to complete the definition, for every efficient attacker's probability A wins must be negligible. Right? So the flavor of the definition is the same as always. there is some attack, there is some game that he is subjected to, that he has to operate in that context. Then there is some events that says, okay, he won, and we want to upper bound this event with that, you know, it might happen that he wins, but it must happen with at most negligible probability, right? Okay, so what are his capabilities exactly? Well, I would say that they are very strong. He can choose whatever message he likes, and he gets to see tags on those. And he can do it for however many times he wants. And then he can present arbitrary message. By the way, I mean, this message also has to be, you know, as this message has to be in the message space. But basically, unless it's in the message space, this algorithm will not work. So, or they will output 0. Okay, so you see, he's unconstrained. This message can be any crazy thing, something that like a real application will never care about. But it doesn't matter, whatever it is, if he managed to create a valid tag on it, valid MAC on it, then he wins, as long as it's not one of these messages, right? So if we didn't have this constraint, it would be trivial. He just makes, you know, M equal to any of these, and he copies this tag here. And by the correctness property, if these tags were created correctly, then of course the verification will work as well. This is a strong property, but I would argue that this is what's really needed. Because in applications, it's, as we say again and again, people don't really control very strongly what it is that they are communicating. They are communicating all sorts of things that you know, they have very little input into. And so let's just give this surrender the power of choice over these messages to an attacker and say, well, whatever it is that Alice happened to send, however crazy these messages were formed, and without loss of generality, let's just make adversary choose them. If attacker is on the wire, right, and he sees all these tags, as he does in the security game, then it means that whatever he tries to stuff into here as a purported message from Alice, he cannot, right? Because this is exactly the event that he stuffed something into this channel, and it was accepted by Bob, even though M star is not in this set, and therefore M star was not sent by Alice actually. There are also the weaker versions of this notion, like for example, that it's not enough for the adversary to choose arbitrary message. He has to choose a message from some reasonable space. Perhaps he likewise does not get to see messages of arbitrary messages signed. Perhaps they have to be within some space, but this is the strongest notion, and that's really the goal. Okay, do you guys have some, is this notion clear? Okay, so let's see how to support it. So one thing is it's actually a PRF immediately gives you CMA secure Mac on short messages. So almost as good situation as in an encryption case, although like a very trivial way of encrypting, just put it through the block cipher. This is the electronic codebook mode, and it has weaknesses. But we saw very, just modified it a little bit, added randomness in a right place, and a PRF implies secure encryption. So let's see that it actually implies authentication as well. So take PRF with keys, key space K. Okay, think of this as just keys of some block cipher, and such that PRF FK, this is family of pseudorandom functions, for example, block cipher, starts at FK, maps, let's say, n bit messages onto m bit messages. Although m is not gonna work that well. Okay, how about t? Okay. Okay. Here is a secure Mac with same key space and message space, which is the domain of the PRF. Okay, except there will be one more requirement. Okay. It's very simple. The sign algorithm, given a key and a message, outputs tag, which is equal to FK of M. Okay, so just run a block cipher on the message. Verify, given a key, a message, and a tag, outputs 1 if and only if FK of M is T. Right? If this and 0 otherwise. So, in other words, Alice, to create tags, simply runs the block cipher with her key on the message and outputs the output block of the block cipher as the tag. Bob sees the message and a tag. He reapplies the block cipher to the message, checks that it creates the same tag, and accepts then, otherwise rejects. Okay, and we basically this example F is a block cipher. So a yes, right, where the message would be 128-bit blocks. Okay. Why is it CMA? Why is it secure? So is it secure? Okay, let's draw a picture. Right, so this was the notion of security. This construction has to survive this type of attack. Okay, so let's see. So a good guy chose his key in the space, in the key space. Attacker chose some message. It's I'm not gonna write it, but it has to be n-bit long. What did he get? He got T1, which was FK of M1. And he can do this any number of times. So let's say MQ was the last query. And he got TQ as a response, right? And TQ is FK of MQ. Okay, so what does he really get? He sends an input block to a block cipher, and he gets to see output block. He gets to see another input, and he sees output. He's querying this FK function on an arbitrary input. And once he's satisfied with all these things, at some point he has to decide an output M star T star, and he wins. A wins if and only if T star. What's the verification? Well, the verification is just rechecking this. So the event that he wins is this one. So, in other words, he is querying the FK, getting values of FK on arbitrary inputs, and then specifies some new input and claims that this is the output of FK on that input, and wins if the claim is correct. But he couldn't have seen the output of FK on that input, right? Because there is a requirement that M star must be not in the set of MIs. So we do the usual, right? If FK is a PRF, then A's view is indistinguishable if FK is replaced by a random function. Let's call it R from N bits to T bits. So rather than seeing FK, he sees the random function applied to M1. And rather than, and that's always, and the keys are not chosen, a random function is chosen. It's chosen at random from functions from N bits to T bits. Right, so this is some, this domain of functions, and it's a random one is chosen. And here too, this relation has to hold, right? And perhaps now you see, okay, there's no more complicated cryptography. There is a random table. These are, inputs and outputs. And apparently, on some M1, it was queried, and some T1 was an output. And how is the T1 distributed? It's a completely random value, right? Because R is a random function. And on M2, some T2, right, etc. So some Q entries in this table, but what is the information in the stuff? None. Because it's a random function. So for every input, it just spits out, random bits. So what is the possibility that on some row that M star is an index to a row in this table, right? Of outputs of this random function. The T star here, there is no information about it. Right, because it's a random function, so every row is completely independent. So what is the probability of success? All of this is useless if you're dealing with a random function. So what is the probability of success? If FK is replaced by a random, is what? These are random T-bit values. each of these, sorry, okay, that's maybe another success greater. These TIs have T bits, each of them, and they're all independent. So what's the probability that this one is in this table? Come on, don't be shy. Oh, I guess I lost you. There's T bits here and N bits in the input. So these things are random T bit values. And they are completely random for each of these rows. So what's the probability that this guy somehow guesses these bits, even though he never queried this function on this row, right? Negligible chance of valid empty. Well, no. So no, it's a wait. Negligible valid empty chance of, well, what is the chance of valid empty? If this is a random function, there is some entry in this table here. This random function assigned to M star some random bits, and A somehow guessed them. What is the probability of him guessing these T bits? No, okay, people, what's the probability of guessing T bits? Yes, it is 2 to the minus t, right? 1 in 2 to the t. Thank you. Okay, so right, because these are random bits. So, and there was this entry was not queried. So you can, in fact, it's not upper or equal, like it's equal, like well, okay, sure. I guess he can like just refuse to answer anything. But really, like whatever he says, if he says some sort of T bits here, then this is going to be the probability he will. There is a 1 in a 2 to the t that it's right. So this has to be rephrased. Say PRF. Is it secure? Yes, as long as T is is greater or equal to the security parameter, right? So that this, in which case this is smaller than 1 in 2 to the security parameter, right? So in other words, if you have a PRF that has very short outputs, it's not good, right? Like just guessing the Mac will work. But as long as this PRF has output of decent size, so if you take a yes, then both the inputs and the outputs have the same length, right? And this is good enough. If you, by the way, take this, even a triple test, doesn't matter. N equals T equals only 64. So the probability that you guess correctly is much lower. And you should take this block cipher is a better choice. Okay. So it's basically rather immediate construction, right? PRF is good for macking. If a PRF is indistinguishable from a random function, a mac that Alice sends out looks like random value. For every message, there is a fixed random value, right? So, but this is not concerned about secrecy. Adverse, here we just say send the message. So there is no secrecy protection. So the fact that the MAC repeats on the same message is sort of not, it's not clear this is relevant at this point because we're revealing the message anyway. And it doesn't matter how many of these PRF values you have seen, you cannot predict a PRF value on any new message. So the whole game is how to extend it to long messages. Okay. It is if you had a PRF that somehow took arbitrary long messages and output values of size security parameter, then above works. So you just do the same. If you have a PRF that takes arbitrary long inputs and is a pseudorandom function on basically all inputs, of course they cannot be too long, right? But they are, because it's supposed to be an efficient algorithm, right? So they have to be polynomially sized. Then the exact same procedure works, right? Nothing changes. It's the same picture. So the question really is, like, you get a MAC if you have a PRF. I mean, at least one way to get a MAC is to get a PRF that works on arbitrary domain. Compare to encryption. We can encrypt short blocks with single PRF that takes n bits and outputs n bits. And what did we do? We ran FK on a random value. This presents something indistinguishable from a runtime pad, and we XORed the message with it. And likewise, we can encrypt arbitrarily long messages with the PRF that rather than have arbitrary inputs, the inputs were still n-bit random values, but we would like it to have very long outputs. So it makes no sense that the outputs are arbitrarily sized, right? Like, I mean, so what is an output? Like, no, but it's just okay. It just makes this very large so that any long message will fit in. And if it outputs like long and I don't need, I cut it. So it's the long outputs. And you can think of counter mode or CBC or OFB as cases of this. It was taking a random IV and somehow expanding it. And okay, CBC didn't do this exactly, but CTR and OFB, yes. And just XORing the message with this long output. That worked for encryption. And in a sense, in authentication, we have like an opposite game. rather than make a PRF, that is somehow takes a short thing and outputs a very long stuff, we want the PRF that does like opposite. It stands on its head. It takes very long stuff and outputs a short value because we don't want these max to be huge. A security parameter is always okay. So it's a kind of a flip of a concern, but it's all in the PRF. There are other ways to Mac, but this is one of this is the source of many standards in this area. So you know what? Actually, let me switch to slides, because now I will, rather than draw these PRF extensions, I will use the ones I have in the slides. Let me just identify which slide set is this one. Okay, no, not this one. Sorry. Okay. Share screen. So do you have the slide now on the screen about message integrity?
Yeah, we do.
Okay, thank you. Okay. So let me show you some constructions. Okay. So in a sense, as this story is repeats in crypto. We know how to do something for small messages. We want to do it for large ones. We have seen it in the case of encryption. We have seen it in the case of a PRG extension. We see it again here. So here is Cbc Mac. This is what you do. Take your message, divide it into blocks, which are the size of the block cipher, so a PRF. And whereas on a short block, you would just put it through the block cipher, and this would be the tag. Here you chain it exactly like in a Cbc encryption mode. You take the output of the block cipher and you use it to randomize the next block. And you put that through a block cipher, and so you recurse. And you don't put this as a tag. You have an independent, the same block cipher, but with an independent key, and that's the tag you output. This last block cipher can be thought of as actually a electronic codebook mode encryption of this value. So you take this value and you encrypt it under an independent key. This is one way to look at it. This is an encrypted Cbc Mac, and this is indeed in the title. And what's inside, it's called the basic or a raw Cbc. Raw Cbc is a PRF. So if I knew that this whole construction is a PRF on arbitrary domain, if I could show it that it satisfies the PRF property, no matter how adversary chooses these orange strings, Perhaps the first orange string has 4 blocks. Maybe the second has 2 blocks. The third has 6. Perhaps the second has the same blocks as the first, just rearranged. So what was M0 in the first message now becomes M1, and M1 goes here. No matter, these values are pseudo-random and completely independent, regardless of any dependencies between blocks. Of course, if you put the exact same orange string, this is deterministic. So the tag will be exactly the same. But there are no other dependencies that this preserves. So this scrambles all other things. It's pseudo-random. The argument that it does goes first, it looks at the green stuff, just the basic CBC. And it is already a pseudo-random function, except we have to, on messages of arbitrary size, but we have to fix that size. In other words, like in this picture, let's consider the raw CBC, but always the orange strings have to have 4 blocks. If that is so, so if adversary has to specify 4 blocks, then this value would be already good. It's a PRF on a domain of 4 times block size bit strings. And the same would also go if I limited myself to 3 times block size bit strings, so triples of blocks. And in which case this value would be an output of a raw CBC. The purpose of this encryption is to stop attacks that have to do with modifying the input size. So here is why can't you just declare this value as a CBC Mac on a single block string and declare this value as a CBC Mac on a 2 block string and this value as a CBC Mac on a 3 block string, etc. The reason you cannot do that is that is a good homework exercise. The exercise looks like this. Suppose an attacker specified some block as the message that he wants to see macked. Suppose that you're running raw CBC and you're hoping it's secure. So this is the wire that he would get as a MAC value. Now he can already win, because if he knows that this pseudo-random function, he has one input-output pair. On this block, it has this value that he holds in his hands. That's the MAC on the single block value. Then he can already win because he can structure M1 so that M1 XOR this tag is exactly M0. And if it is, so simply he makes M1 equal XOR between M0 and T1. And the T, let's say T0. Let's call this value T0. If he does so, then running the CBC, the raw CBC Mac on a new message that has 2 blocks, M0 and M1. Well, on M0, the value is, this wire is the same as before, right? This is deterministic. So this is T0. T0 XOR M1 is M0 because that's how he chose M1. So what's the value here? Well, this is a block cipher. On the same input, it has the same output. So this will be T0. So therefore, he forges. Having seen a single MAC, a MAC on M0, he forges a MAC on a 2-block message, where the second block is an XOR between M0 and T0. And he can predict that the tag on that is the same T0 that was the tag on M0. So that's why the raw CBC doesn't work. And notice the attack used crucially that the scheme was used on different sized messages, that somebody used the raw CBC first on a single block message, and then nevertheless they also use it for a 2-block message. I mean, the verifier actually used it for a 2-block message. This would always break if you allowed people to run raw CBC on variable size. Like if in some construction, for some reason, these block sizes are fixed, then I guess you can run a raw CBC, except that you would have attacks if at any point somebody somehow messed with the length of these things, which would happen in practice. So why do that if one more block cipher stops attacks connected with it? So you can also see intuitively that this encryption is going to stop attacks, because now Mac on M0 is this T0 wire, but not in itself. It's the T0 wire encrypted under using this block cipher. So it's an FK1 encryption of T0. And that's what he sees. So, and since he doesn't know K1, he cannot reverse this to get this wire and apply the same attack. In other words, he doesn't see these wires, he sees their encryptions. And if this is a pseudorandom function, then basically this separates the outputs from these inputs successfully. The only thing that would happen is that would go wrong if there is a collision on this output wire with some previous ones. Then the output here, the MAC on this, which was an encryption of this wire, could be reused. Because, well, if there is a collision between this, say, wire and this one, then that tag, it works correctly as both a tag on all this message and a tag on just the first block. So it's the collisions that the argument has to argue are not happening. Okay, that they are, if f is a pseudorandom functions, and the probability of encountering collisions here, no matter how you structure these messages, is low. So before, here's an alternative design. It's called nested MAC. You chain differently. Assume, for simplicity, that you have a block cipher like AES, whose keys are 128-bit block messages, and plain text blocks are 128. So you can think of an output as a new plain text block, kind of like here. It's not exactly plain text block, it's just an XOR pad with which you XOR the previous block. But you can also think of them as keys, as new keys, because they have the same 128-bit size. So that's what nested MAC does. This thing in cryptography is called a cascade. I start with a key, I encrypt first block, and I treat the output as the new key, with which I encrypt the second block, and I treat the output as a key, with which I encrypt the third block, etc. And again, the raw cascade is not secure as the MAC. So I do the same as before. I just encrypt it. And this is needed in case keys are shorter than plain text blocks, which was, for example, a case for DES. Keys were 56 bits and input blocks were 64 bits. So you had to pad it. But for AES, there's no FPAD. let's look at what happens if you attacking cascade is even simpler. Although let me just go over this on a picture. It's much easier. So what would happen if somebody outputted this wire as a MAC on string? Oh, sorry, this is stupidly ordered. It's this 013. Okay, it should be 012. So please disregard that. If this wire was a MAC on these 3 blocks, then I would forge I would be able to create forgeries on messages, arbitrary messages, whose first 3 blocks collide with these, but the next blocks are up to me. I can make them anything I want. Why is that? Because if this was the MAC, so an adversary who says, okay, please MAC this 3-block message, and he gets this value. It's a cascade. This is a key. He can continue computing this on arbitrary next blocks. The cat is out of the bag. It's like you gave him an internal wire that you use yourself to continue computation. So he would be able to use this. He doesn't need to have this key. As long as he forges MAC, as his forgeries pertain to messages whose first 3 blocks are exactly these, then, well, this construction would recompute the same key here because it's deterministic. So he doesn't need this stuff. He only needs this value to continue the computation on arbitrary messages, next messages on his next blocks of his choice. So, so this is the cascade stuff. If I hold in my hand a cascade applied to any number of blocks, I can continue the computation, meaning I can compute this cascade on arbitrary message whose first blocks coincide with these, but afterwards it's my choice. It's arbitrary W, arbitrary continuation of these first blocks. So that's the encryption stops that. And to argue that this is all you need, that this sort of second layer of encryption stops all these attacks, it's not so easy. But you know, so we will not do these arguments. But I sort of hand waved it. In terms of their exact security, they act very differently. Encrypted CBC is easier to analyze. In fact, it has a tight relation to a security of the block cipher. Because again, any interaction with this encrypted CBC can be emulated with a box that just says, okay, oh, you wanted me to compute for this following first block. So I'm going to query a block cipher challenge. If it is correct, you know, I'm getting this wire, and therefore, and here I'm going to query this, and I'm going to query that. So the reduction queries the blue box. It's either a random or it's FK. If it's FK, it replicates this. And if it's random, you still have to show why random function works. But if you use random function, you can basically argue that this value is random, and so is its encryption. So any attack is an attack on the underlying PRF, which you show here. So whoever has an advantage, and by the way, this is, you see here explicitly, I'm claiming that this encrypted CBC is a PRF on arbitrary messages, and therefore the previous argument is going to argue that this is a Mac on arbitrarily sized messages. And what other attacker exists that claims to have certain advantage over the PRF property of the encrypted Cbc Mac, it cannot be larger than an attack on a underlying PRF, the little blue box that is used within encrypted CBC. But there is also this bound. Now, what is this bound? It's a birthday bound. It's a collision bound. You have Q queries. And it's with every query, if this was a random function, then these wires would be kind of chosen at random. But if there is collisions within these wires and within especially this collision, then you cannot host. Because if this ever pricks the same, you think of the blue box replaced with a random function. That's the first step in the analysis, as always. If this value was just a randomly chosen one, well, then there is a probability that it collides. And once it collides, you will kind of host because this value, this tag is as good as a tag on the, whatever two orange strings there were who created the collision on that wire. So the best you can hope for is this stuff is random, but you still cannot do anything about collisions. And now, if you choose Q values at random from a space of domain, or range of the PRF, and here you assume that the range, domain and range are the same. So it is a block cipher from n bit to n bit. Then what's the probability that you encounter collisions? And it's the birthday probability. It's a square of the number of these things over the domain size, right? So what's the birthday thing? Let's say there's 356 possibilities of birthdays. When is the probability that people in the room, there's two people who have the same birthday? Well, it actually goes with the square of the number of people. So once you have 20, this is 400 divided by 356. So it's very close to, of course, it cannot be more than one. It's just that it's very close to one. So this is an upper bound, it's not an exact value. Likewise, if you have a block cipher that has only like this, who has only 64 bits of output, then this will be essentially 1 after just 2 to the 32 queries. So 4 billion. And if you are just like a person running an HTML on one session, okay, you probably, unless you're some complete maniac, you are not going to send 2 to the 32 packets on a session. But if you're a VPN and you're macking, tons of traffic, then you should be aware of these limits and refresh a key. Or move to a more modern cipher where this is 128 bits. So now security holds for, up to a much larger number of messages. And this basically, you're not going to use a key for that long, or you would basically burn. Now, is nested Mac, the colliding elements are not plain texts. It's also all about collisions on these wires. But here, the collisions are on keys. So again, the best you can hope for is that you have security as long as nothing here collides across different invocations. So think of this invoked on different orange strings of different sizes as well. And you want these wires not to repeat. Okay, I mean, they will repeat if you have some blocks the same, right? But okay, that you can help, if you fork, then it should have completely random values. But there is always probability of repeat. Well, this is this probability. It's again number of queries over the, the exact constants here are really immaterial because, there is something in the security arguments that somehow needs to think of this twice. And there is something here that doesn't. Okay, but these are just constants, so it doesn't matter. It's the number of queries over the key size. And I skipped this part in the last lecture, but check it on the slides. It's a DES is antiquated, has two short keys, but there is a way to extend the key size, and it's called triple DES. So keys now are basically triples of keys, and they have 3 times 56, so 168. At which point this construction is actually more attractive. This bound is going to be stronger, okay, as shown here. Okay, and as I was arguing, these bounds are tight. So basically, because it's a collision probability, once you have this many, then you are going to encounter collision. So the big PRF that this creates, either encrypted CBC or Mac, is going to have a collision. And you might not see immediately why a collision is so deadly, because you see, an attacker, why is collision bad? Okay, so the immediate thing is that, well, why? Because the tag on message M is apparently the same as the tag on message M prime, because M and M prime collided on this value, and therefore they collided on this value. But how would the attacker know that? He gets to see, he says, okay, please mark M. He gets the value, the mark on M. If he knew that there is an M prime that collides with M, then he would submit this as a forgery. But he doesn't exactly know that. And if he tests that, if he sends M prime, then he sees a collision, but it's too late. He already marked both of these messages. So a mark on M prime does not really constitute a forgery, does it? But it's worse than this because of the following. These constructions are extendable, meaning once they have a collision, then the same constructions on inputs that append the same postfix, call this postfix W. So think of X and Y as two messages. They actually don't have to have the same sizes. Like say X, is some 1000 bits and Y is 2000 bits. If there is a collision in the Cbc Mac or Mac on these two, then the following is true. These collisions will keep happening, meaning if I form a message as X followed by arbitrary postfix W, then it will also, Mac or Cbc Mac will collide, will have the same Mac as Y followed with the same postfix. This fact is easy to observe. I mean, You see, because what does it mean that an Nmac, let's say, collided? So this tag was the same for two orange messages. Call them M and M prime. If this tag was the same, therefore, except for negligible probability of, well, this is a permutation, so it's just impossible. Like this value must have been the same, and therefore this value must have been the same. So this wire was the same. Now think of this wire as here, okay? Because I cannot easily continue. Now think this. So the two orange values, X and Y, were some blocks here. Now, if X hits the same value as Y here, then after this value, if X is followed by whatever, and Y is followed by the same whatever, then this computation will follow the same path, because that wire was the same on X and Y. So if we feed them with the same whatever postfix, all these values will repeat, and therefore the tag will be the same. And the same goes for Nmac. You know, if this wire is Cbc Mac, if this wire is the same, then again, no matter what this is, if there were two block messages that created collision on this wire, these collisions will keep on continuing. Maybe that's an exercise. Why is this creating an attack? So this is all you need to know to create an attack on forgery on unforgeability of a Mac. If someone finds X and Y for which this is clear, then this fact allows you attacks. Okay, so just okay, think this through. I will leave you with this one. Okay. Thank you for listening. I will kill the recording. And you're welcome to ask questions if you're still around and you want to do so. Okay, thank you, everyone. Thank you, Justin. Thank you, everyone. See you next week.